Good morning, ladies and gentlemen. Let's talk about springs.
But it's fall.
Spring basics. Fall basics. No, spring basics. Okay. The first two are just little FYIs. The stress is the force that you apply to the spring, and the strain is the change of length. The bottom two are more important. The equilibrium and restoring force, which we touched on in our hacksaw lab. Equilibrium is the unstrained position where it's at equilibrium, and the restoring force is when, if you think back to the hacksaw lab, it was seeking to return to that middle equilibrium point. Right. So what do we do with this? Hooke's law. What is Hooke's law? Hooke's law is says the restoring force of a spring is proportional to its displacement from equilibrium, ideally. So what this means is, here's a spring, and it says is that the further you displace a spring or distance that you create in the spring, the greater the force, and you can feel it. Right, the force is getting greater. So that's what our proportion tells us, but we can't really use that.
What does that negative mean?
The negative, the negative tells me whatever direction the force is in, the displacement is in the opposite direction.
Well, the farther, so you're pulling it that way, and it's trying to pull back this way.
Yeah, so it's kind of a direction type thing. Well, it's not direction, but
It is.
it is direction.
It is.
But we can't use this, right? This is a proportion.
Yeah, we need something.
We need something. What are we missing? Well, our constant of proportionality, QK. Where K is the spring constant for that spring. So every spring has a spring constant, and
It's like for the same amount of displacement, you get more force or less force depending how stiff the spring is.
yeah, and every spring has a different spring constant, like we talked about, depending on the stiffness, and you can calculate it.
Yeah.
And so we can use this equation: the force of the spring is equal to the spring constant times the displacement. Okay, so we just threw in that spring constant. Okay. Practice problem. A hand exerciser uses a spring to resist compression. A force of 89 newtons is required to compress it by that many meters. What is the spring constant? Pause it. Try and do it.
Okay.
And we're trying to figure out
Okay.
this. I'm just going to divide it by x. So 89 newtons divided by 0.0191 meters, and I get 89 divided by 0.0191. Is that right?
Yep.
Meters, and I get 465. I'm gonna call it 4660.
4660.
Yeah. Ignore my
And
lack of.
what would the units be?
Well, it's a constant, right?
It would be with the same thing you got on the equation there.
Newton meters. All right, let's
Newtons
start here.
over meters.
Oh yeah, sorry, not Newton meters. Newtons over meters.
So you want to stretch that thing out 1 meter, you got to put in 4,660 newtons.
Fine. Okay, so and again, that negative, whatever direction the displacement of the string is, the force is in the opposite direction.
Yep.
That's what that negative means.
Yep.
Okay. So how could we find the spring constant of the spring scale? So, did I forget to show them these? I haven't showed them yet. So we have our soft scale, our medium scale, and our a little bit harder or stiffer scale.
You see the size of the springs in there.
Okay. So how could we find these? How could we find the spring constant?
Well, we need to have the force of the spring exerts, and we need to have the displacement.
Okay, so I could measure. So this spring has the capacity to do, let's see, so this is going to be 5 newtons right here. And I'll go ahead and measure from this side. I like to measure from the same side here. and we have 5
It's
centimeters
like 5 centimeters.
for 5
5
newtons.
newtons.
Okay, so 5 divided by 5, that would give me a spring constant of 1, right?
1 Newton per centimeter.
Yeah.
Yes,
Okay, so then we could do the same thing for this one, right?
the brown one.
The brown one. So let's see, for every 5 centimeters here, I have 10 newtons, it looks
Well,
like.
it's the same displacement and 10 newtons this time.
Okay,
that'd
so
be-
10 divided by 5?
10 newtons divided by 5, that'd be 10
Two.
divided by 5 is 2 newtons
2
per meter.
meter. Okay, last one. Okay.
The big boy.
There we go. Okay, so we got 50 newtons for 5
5
centimeters, so that's
50 newtons divided by 5,
10 newton meters.
that'd be, yeah,
Okay,
10
so
newtons per meter.
bigger spring constant, stiffer
spring.
spring.
Now, if you were here in the classroom, you could play these springs and you'd feel them for yourself.
And you would have had to figure that out by yourself,
That's
too.
right.
Okay. Oh, and here we go. So we have our 3 springs. Oh.
Yellow, brown, and green.
And so this is a force, and delta x is over here. What could we figure out by looking at this graph?
Well, for the same displacement, you get different forces depending on which spring you get.
So for the yellow one, if I was looking at the slope of this line, what is the slope of the line represented by mathematically?
The rise over the run.
Okay, so the rise over the run, force over delta x, doesn't that give me the spring
That'll
constant?
give you the spring constant.
So the slope of the line is going to be our spring constant.
That's right.
And we know that this one has a higher spring constant, we just measured it, and less high and the lowest right there. Looking at the slope of the line, we can see that. Are you doing work when you stretch a spring?
What is work?
Work was force times displacement. Okay, we just saw a graph that looked like this. Force and displacement. Well, when we calculated the displacement with a velocity versus time graph, that was just the area under the curve, right?
Oh,
Right? Now we've got a force versus displacement. Isn't force times displacement work?
yes, it would be. So how could you find the work here?
We could just do force times displacement. And we could find the area, we could find the area under the curve and we could find the work.
That would be equal to the work done extending it to that point.
Yeah, okay. Well, I think that's all, folks. Your homework tonight, ignore this, is... Go back, look at it straight. Oh, wrong way, that's right.
I don't think you've got it up there.
That's okay. The homework tonight is this right here. Page 274, numbers 1 and 2.
Well, that's easy.
Easy peasy. Lemon